Hi, everybody. Happy Hanukkah to everybody. In Hanukkah and in these holidays in general, we are celebrating miracles. Nes Hanukkah, the miracle of Hanukkah. Since we discuss science, I am not ready yet to discuss miracles. But in science, we often not necessarily talk about miracles, but talk about paradoxes. And I thought that I'll skip that, but I thought it would be in the spirit of Hanukkah, maybe the closest that I can talk about miracle is talk about paradox in science. And since last time we discussed quantum mechanics and how to make sense of it, I'll repeat this in the context of the famous EPR paradox. EPR is Einstein, Podolsky, Rosen, published first in a paper in 1935, Physical Review. Physical Review already existed at that time. The title was, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? And that actually, that kind of paradox was raised by Einstein 10 years before that. And it ignited a long series of debates with Niels Bohr. You can see both of them here in this picture. A series of conferences and letters and articles back and forth about the interpretation or the consistency of quantum mechanics, and so on. Okay, so I would like to spend a few minutes at the beginning of today's lecture about this EPR paradox and to show you how it is kind of dissolves away using the consistent quantum mechanics that I described last time. So actually, this paradox itself is kind of a Gedanken experiment, a thought experiment, often being done in physics. But it's not even clear what, there are various interpretations of the paradox itself. So it is not only interpretations of quantum mechanics, but also interpretations of what Einstein and Podolsky and Rosen actually meant, or what is the force of the paradox, or whatever. I'm giving you, for brevity, I cannot give you an historical account, it will take lectures, but I'll give you a version, a compact version, which is kind of, was elaborated later on by David Bohm and others. Okay, so here is this compact and very simple version, I'm sorry, which is showing the famous Alice and Bob doing a spin measurement. So here is the paradox. Imagine you have two particles. Each one of them has spin 1/2, the ones that we discussed last time. But now the system together is a vectorial. The total spin of the system is a vectorial sum of S of the particle A and S of the particle B. And the system is prepared in a state where the total spin is 0. And since we assume we assume conservation of spin, that there is no process that violates conservation of spin, conservation of angular momentum. So if the system was prepared in a state where the vector S is 0, this conservation law should hold throughout. Okay. So imagine that we prepare the system like this in the source, and then we send Alice to, I don't know, one corner of the world with the particle A, and we send Bob to another corner of the world, the opposite corner of the world. They don't meet. Anyway, to a flat universe, a flat Earth. anyway, far away with particle B. And the assumption is that throughout there is no change, there is no interaction, or no magnetic field, spin is conserved, everything is fine. Good. But now Alice has a lab, magnetic lab, with a magnet that can measure the spin either in X direction or in the Z direction. And Bob similarly has his own magnet that can measure spins in the Z direction or in the X direction. Okay, good. Actually, okay, fine. So we can write down. So that's kind of classical story. But we can write down a initial quantum wave function, this psi 0, which is called the singlet state, doesn't matter, which is a superposition of a spin sz plus and minus of the two particles, minus the superposition of z minus and z plus, and that a state which you can show that it has spin total spin 0, because if SA is plus, if ZA is plus, ZB is minus. If ZA is minus, then ZB, I'm sorry, there is plus here, which is missing here. So this is a state which is consistent with sum S equal to 0. Now, of course, it's easy to show, we can also write it in terms of X, in the same argument, because the total spin is 0. So again, if you measure XA plus, then XB will be minus, and if you measure XA minus, in other words, this superposition of these two states, again, you should be here plus and here plus. So what is the paradox? So here's a simple version, okay? Imagine, and I'll stick to this scenario throughout, that Alice measures at some time later on the spin of her particle in the Z direction. And at the same time, Bob is measuring its particle spin in the X direction. Okay, so here is the conundrum. Alice, let's say, finds that ZA is plus. Let's say this is the outcome of the measurement. Okay, but then because of the conservation laws, it's immediately known that the spin in Bob's particle is Z minus, right? Because if one of them is plus, the other one must be minus. Conservation law. Now, is this a problem that we have information that Alice knows about the spin at Bob's location once immediately when she does her measurement? Is it a problem of locality? Does it show long-range correlations or something? What do you think? Is it a problem already? Chiani, what do you think? Is it a problem that Alice measures the spin ZA and finds plus, and immediately she knows that the spin B is minus? And there is no, the distance is far away, there is no, it's you know. Is it a problem in terms of violating locality? Can we stop here and say this is a paradox? Often that's what people think, that this is the paradox, basically, that there is a long-range coherence, the wave function is coherent over long distances, so you measure in one part, you know the other part, and there is a paradox here. It's kind of violates locality. Quantum mechanics violates locality. Is this a valid argument, Jonathan?
I don't think so, because there is no direct effect between the two dots. So you can say, you can take a very large system with energy conservation, and even if it's not quantum, if you like, you know the energy is raising in one part of the system, you can know immediately that in other part there is a decrease, even though there's no effect and no information travels really between the two dots.
Yeah, you're absolutely right, except that I wouldn't say, if you measure a decrease in the energy at one part, then the energy will not, then the effect, the process will have to will have to travel, because you are looking at the perturbation. But here it's not so. You're not looking at the perturbation. So imagine, it's purely classical phenomena. Imagine I have two envelopes. In one of them I have a red card. In another one I have a blue card. I shuffle them. I don't know which one is which. I send them to Alice and Bob. They know, and we know, and all of us know that if one card is red, the other card is blue. So when Alice has opened her card and finds it's red, then she immediately knows that the other one is blue, right? This is correlation. It's not causation, and it's clear in classical phenomena, and it's not a paradox, as Jonathan said. It's a knowledge, because the events, the two pieces of information, or the two physical entities, are correlated, are prepared to be correlated. So you know one, then you know the other. So this is not, I just want to say, this by itself is not a paradox. Okay, good. So we know that Bob's spin ZB is minus. But now imagine at the same time, Bob's measures the x direction of spin of particle B, and he finds that it is in, I don't know, in minus direction, whatever it is. Okay, so now there is a problem. Why? Because now we know about the particle B. At the same time, we know both its z direction and its x direction. But that seems to violate quantum Heisenberg uncertainty, because x and z are non-commuting. So we're not supposed to be able to determine the value of a spin simultaneously in both z direction and x direction. That's one version of the paradox. This is purely quantum paradox. There is no classical version of that. Uncertainty principle prohibits you to determine both of them, SZ and SZ and X. Okay, so that's a paradox. Are there questions up to here? All right. So it's one version, but it's very compact and very simple. And what I want to show, how the consistent framework of quantum mechanics makes this paradox, disappearing. Okay, why? So let's for the sake of here it is. Okay. Let's first add the measuring device of the two particles. So we have psi 0 as before, and we'll talk about the z basis just for convenience. And now let's add the z measuring device, ZA of Alice A, and similarly B, so XB. And as before, I mean as last week, we assume that if A is ZA plus, then there is some initial pointer at rest, ZA, and then it moves to the plus, and ZA is plus. I just write it capital ZA plus. It already implies that also little ZA is plus, just brevity of notation. And similarly, the dynamics, and we assume the dynamics of the interaction is such that if the spin X in the B location is plus, and the device starts from 0, from rest state, then the device will go to plus, and also little x will also be plus. Okay, so now we assume that the initial state, capital psi, the combined state is this spin state, singlet, little psi, times the rest state of the two devices. That's the initial state. Okay. So now we are to be clear that we are not talking about a measurement that makes perturbation on the system, destroys information, all this garbage. We will be very clear. We will have the initial state size 0. We will have the final after the measurement on the right-hand side. We'll have the framework that describes in the basis of the device measurements, right, the outcome of the measurement. So capital Z is plus or minus, and capital XB is plus and minus. This does, we're using a framework where the elements of the framework are the possible outcomes of the measurement, as we discussed last week. And then we have some intermediate state, which we are discussing about, okay? What does it mean? We have the initial state size 0. We have the final outcome of the measurements in this framework. And then we're asking what happened in between. What can we say about the spin in between? Just to make sure that we're not talking about after the measurement and the measurement destroyed something. Let's ask, what have we learned from the measurement about the spin of the system at some intermediate time? So this is this here. Okay, so this is now framework 1. Framework 1 says, after we're doing the measurements, we are using a framework in this intermediate time. We are trying to guess what is the spin Z in Alice places and what is the spin X in Bob place. ZA and XB. That's what we're trying to answer, okay, to infer. So it's very simple to see. Since Alice made a measurement in the Z direction and find, so the conditional probability that little z in the intermediate time beforehand was plus, it's 1, because that's the outcome of the measurement. And similarly, if she finds ZA minus, the probability that ZA, that the spin A in T1 was minus is also 1. Okay, that's simply just saying that since nothing happened in between, there's no interaction, then that's the answers that she can infer from her measurement. And similarly, Bob can infer from his measurement that the spin in the X direction prior to the measurement was the same as what the needle indicates. Is PXB is plus if the measurement says plus, if PXB minus if the measurement was minus. So far, so good. What do we know about the spin Z at time, in this intermediate time, upon the spin Z in Bob? Because that's what the paradox, right? The answer is we don't know anything. We do not know anything. Why? Because ZB is not part of the framework, of that chosen framework. So the paradox doesn't even start, because the paradox said, you know that XB was either plus or minus, Bob knows, but at the same time, because of conservation law, it also knows that Z is minus, let's say. The answer is no. Conservation laws are within a framework. You cannot apply conservation laws to answer questions which are not legitimate, which are outside the framework. Since ZB is not part of the framework of this framework A, you simply cannot say what is the probability of it. You cannot say it's -1, you cannot say +1. It's not a question, it's not part of the sample space of framework A. Now you can, and similarly for X in the A dimension. Similarly, now you can choose another framework just to show you, you can manipulate and see what, okay, so framework B is different. Here, we are actually, the set of questions, the element of the subspace does contain ZA, like here, like above, but also ZB. Okay, so now we can supposedly talk about XB and ZB, because XB is the measurement in B, and little ZB is one of our elements in the subspace. We are legitimate in asking questions about it. Now let's be more careful. So now we can say that probability of ZA plus, if the needle was plus, was 1, and the probability of otherwise it's if it was minus. But now we know from the conservation law that if ZA plus, if ZA is plus, then ZB is minus. So this is probability 1. That's fine. That's conservation law. Now we can apply conservation law, because in the process between T0 and T2, we are using a framework where we are legitimately asking about the same component, the same Z A in both times. So there is and ZB, so there is a conservation law. However, now we cannot say anything about X, because although the needle has XB plus and minus, but we don't have in the intermediate state, we don't have an element on the subspace about X, either XA or XB. So now we cannot say anything about the X direction in the intermediate space, in the intermediate time. So we have to choose. Either we are using this up framework and we can know what happened before the measurement about ZA and about XB, but not about X and Z in the same spin. Or we're using a framework where we can talk about what was both spin Z of A and spin Z of B using the conservation law, and then we can use the conservation law, but we don't have any information about X. And now you can also use other framework and so on, and exhaustively analyze this example, it's a very simple example, to see that if you keep the rules strictly, not like we would do it in the Corona time, single framework, or in the process, single history, then even conservation laws cannot sneak through. You have to use conservation law only when you are using the same quantity in the same, following the same quantity in the same history. Then you can say it didn't change. But if you are using this quantity T1 and another incompatible one in T2, then there is no conservation law even. So once you use this paradox dissolves. It simply it assumes that you can ask, you can talk about what was the spin of Z of one particle, both Z and X, and there is no framework that allows you to do this. Anyway, so quantum mechanics is bizarre, as I said, because it has this framework and you have to choose a framework. You know, that's bizarre, completely non-classical. But within a framework, everything is kind of logical and probabilistic, and obeys conditional probability, as I showed here, and Boolean logic and conservation laws and everything. Okay. Okay. Hanukkah paradox, EPR. There are books, there are conferences, there are articles about EPR paradox and quantum long-range coherence and violating causality and all. It's a very rich, and Bell inequalities that we mentioned last time. It's a very rich field. I'm just giving you a snippet and to show you how this kind of consistency, if you apply it rigorously, you have very systematic and very consistent way to apply quantum mechanics and to avoid paradoxes. Good. So let's now this was just a pticha for the main lecture today, which is quantum mechanics and the brain. I want to go back. I want to move my way through to the brain, and there are two parts to this lecture. The first part, I want to ask how we go from this bizarre framework, incompatible superpositions, and so on, in the micro phenomena to the macroscopic phenomena. After all, the macro phenomena doesn't seem to really, you can choose different, different frameworks. Basically, you choose the classical framework, coordinate, momenta, angular momentum, everything is fine. Doesn't seem to have this freedom of choosing framework which are incompatible. It's all gone. So how do we generate a transition from micro to macro with quantum mechanics? It's even worse than classical. In classical mechanics, even on the statistical mechanics or thermodynamics, the phase space, the rules of the game were the same. Just the question was, how. But here it looks like classical mechanics is very different language or very different ontology than classical mechanics, than quantum. Macro has different ontology than micro. The phase spaces are different. So what's going on here? That's one part. And the second part, hopefully I'll get to it, is once we understand how the macro classical or semi-classical emerges from quantum micro, we can discuss to what extent, what are the lessons about the brain? Is quantum brain real or not? To what extent? Okay? Okay, Schrödinger equation. Okay. I want to start by highlighting a point which I already said last time, but I want to repeat it to highlight a point. If we talk about spin 1/2, that's, and we just take the Hilbert space, Z plus here and Z minus here, and we just take an arbitrary state, just draw a vector in this two-dimensional Hilbert space. I call it psi. It does an angle theta with the Z with this Z plus axis. Okay, arbitrary. Okay, so I can write it in this fashion: cosine theta times Z plus, cosine theta times Z minus. I emphasize the way I write the wave function doesn't really commit me to a framework. This is just a mathematics. I just choose a basis to write my W. W is here, but in order to answer physical questions, I have to say which framework I'm using. Okay. So one framework is framework Z. Okay. Then I know that with this psi, I can answer questions about the probability of being in the Z direction, which will be cosine square theta plus, or to have a Z minus, which is sine square theta. This is Born rules. Okay, that's one interpretation. Okay, another not interpretation. One physical, one framework from which I can talk about probabilities. Now I can also do something. I can say, well, imagine I take this psi and I take another psi which is perpendicular to it. I call it psi perpendicular, and I use this as my framework. Why not? In other words, there is a matrix for which this is one eigenvector and this is another eigenvector. Good. What can I say in this framework? Well, I can say that the probability that psi occurs is 1, and the probability that psi perpendicular occurs is 0. Good. But I have also a more physical interpretation of what it means. It means, in this case, that the probability is 1, that the spin in this direction is 1, and the probability that the spin in this direction is 1 and is 0. In other words, this is like Z and, but rotated. Or you can think about this as plus and this is minus. Okay. Why I'm bringing this example? Because this example shows you that in purely quantum small system, microsystems, all these possible frameworks have similar interpretability. Either I'm looking at the probability in the z direction, or the probability in the x direction, or the probability in some arbitrary angle, whether the spin there is +1, -1. So it depends on what do I want to measure, what I'm interested in. This will determine my framework. If I have a machine measuring z direction, I choose this. With the machine measuring some angle, I use this, and so on and so forth. All these frameworks, I have the same intuition behind them. Now let's add now our device D, and assume the device D is a macro machine which has a large high-dimensional Hilbert space. And as I said, out of this high-dimensional Hilbert space, there are three nice ones, macroscopic ones: Z, pointer states, Z plus and minus, but there are Z and other, of course, Hilbert space, possible states, of course. And then our little spin half Hilbert space. And now they're interacting, okay? And now we have this, as we spoke as previously, we start with psi, let's say in the x direction, and now it interact with the machine, and we have this what's called entangled state. Entangled because now the spin is entangled with the states, with the two orthogonal states of the device, D plus and D minus. It's the same as the two particles entangled when they are starting. But here it is our little spin with this macro state, D plus and D minus. Okay, now let's talk about framework. So if I use the ZD framework, then it means that the probability that the machine would show plus and the Z spin Z will be plus is 1/2, and the machine with minus Z minus 1/2. I know what it means. I know what a pointer state plus means, and it makes sense. If the pointer state plus is plus, then my spin is plus, and so on. Now, what happens if I decide to choose, like before, this framework, p size 1 and some perpendicular subspace in this combined Hilbert space, minus to probability 0. It's also a framework called unitary framework, also a legitimate framework, like in the spin case, but now in the SD. However, it has no interpretation because we don't understand, we cannot, not we don't understand, we understand the mathematics of it, but it means we cannot say anything about the spin, the little spin S. We cannot say anything because we just say that the two systems are in this entangled state, and that's it. We cannot interpret it in our language, in our macro language. We can interpret pointer plus and pointer minus and pointer 0 and our little spin accordingly plus or minus, but this entangled state is fine, it's a quantum state. Like the Schrödinger cat is legitimate to insist that it is in this quantum state, but then we cannot ask whether it's dead or alive or half a dead. There is no dead and alive, and there is no cat in this framework. So you see here, you see that there is difference that when you couple a quantum system to a macro system, and you want to interpret the result, the state, in kind of in a macroscopic language or interpretability, there is already a preference framework and non-preference. Most of the frameworks are not preferent because most of the framework will be this kind of entangled state. They're not interpretable. If we want to make sense of what the spin is, we have to choose this framework ZD. Okay. Good. So that's the beginning of emergence of macro. You can see that macro forces, if we want to make sense of our macroscopic world, it forces upon us to use a framework which have macroscopic interpretability. Like in the cat, if we want to open the box and ask whether the cat is dead or alive, we have to use a framework where dead and alive are the element of the sample space. Okay, so I'm going to use this, but now to go one step further, which is what happens if the same setup, but instead of D being a measurement device, B being a macroscopic system like a heat bath or some big environment which interact with our spin. Otherwise, it's the same. Okay, so the environment will have the same property that when the spin interact with it in the Z direction, if it's plus, the environment will go to a plus state. And if it's minus, the environment will go to minus state. In other words, we again assume that the environment doesn't change, like our D doesn't change the spin, but the spin affects the environment. So here it is. I mean, the same algebraic set for E is now environment, not okay. And now we are using, let's use the preferred, here we said this is the preferred framework because we know what it means. And let's use here this preferred framework. But now we are in a problem. Because what is the preferred framework? It is that the probability that the spin is in the Z direction and the environment is in the plus direction is 1/2, and the spin is in minus and the environment is minus in 1/2. But we don't know what the environment minus and environment plus is. The problem is that unlike the device where it has these nice pointers, the environment is opaque. E minus and E plus are just two quantum states of the environment. They don't necessarily, I'm not assuming, you know, it is some configuration of the spins or the position of the particles in the environment. So there is we cannot use this as it is to ask conditional probability. What we want to know, or marginal, want to know, for God's sake, what is the spin of our particle? Is it plus or minus after the interaction? We have kind of to integrate out or condition, not condition here, it's actually integrate out. In the device, we did condition because we know what it means. Here, we want to integrate out the environment. So the point is that when a particle, a quantum system, interact with a macroscopic complicated quantum states, then in order to make sense, it's not enough to use a preferred framework like this. The preferred framework is a framework where we integrate out these quantum degrees of freedom of this environment. This is actually how we get a macroscopically interpretable answers. What we want to do is marginalize over E. And then we can get meaningful answers. What is the probability that the spin after the interaction is in plus direction or minus direction? Okay, so how do we, so this is what it called coarse graining. Coarse grain framework. We already heard it, we discussed it in statistical mechanics, how you go to probabilities, macro with coarse grain. It's the same, but now in a micro, in quantum mechanics, okay? So now within quantum mechanics, we want to do similar to what we discussed in classical mechanics. We want to integrate out this heat bath or environmental quantum states now, which we are complicated. We don't know. Next time we'll do it, it will be another state. We're not interested in the joint probability of Z plus and E plus. We're interested in the marginalizing out, averaging out the environment quantum mechanics. Now, I don't want to get into the details, but I just tell you, some of you may know, but those who don't know, I'll just tell you how you do it in quantum mechanics, how you do coarse grain. In classical mechanics, it's just average, okay? But here, there is something which is called density matrix. Basically, this is pure state, psi. Capital psi is this one, is the combined spin and environment state, the entangled state. It's a pure state, entangled state, just a state, a vector in combined Hilbert space. But now we want to trace out on this projection operator. Remember, each vector in state space, in Hilbert space, is associated with a projection operator by a matrix which project arbitrary state to this direction. So this is this matrix or this operator corresponding to the pure state psi, and we just trace out the environment degrees of freedom. Okay, and you can do, and then if you do this properly, you get now a new matrix, a new operator, and now you can apply Born's rule as if it was if it was psi, right? So Born's rule says, you know, take psi and project it onto z plus and take squares of this, right? So it is like z plus psi transpose z plus transpose, and this will be the probability. And now you can do it also here. You can take the matrix rho psi, this new matrix, and look at the element in the basis. Well, either you compute this or you look at the basis, so it will be one element in the matrix and so on and so forth. So this is the recipe how you integrate out degrees of freedom from a pure quantum state and generate a coarse-grained operator, rho. So again, each pure state, each vector, you can associate with it as a projection operator on this state. Now we generate another operator, another matrix, by tracing out the environment degrees of freedom. So now it's like marginalizing in statistical, in classical probability. And now we have this rho instead of the psi, and now we can apply Born rule. That's the recipe in quantum mechanics, how to compute quantum statistics when you integrate out some of the degrees of freedom. Okay, now let's see what happens in our case. I want to go back here. Remember, we want to marginalize out the E. So if you do the algebra, it's relatively simple. Just take this psi, you take this one here, up top here, you take the row column, and a row vector, column vector, and you integrate out the E, and you get this row here in the Z basis, you get this matrix. This is the density matrix where alpha now is this part, the off-diagonal elements is the overlap between the two environmental states, E plus and E minus. Remember, the entangled state have these two E plus and E minus, coupled, entangled to the spin plus and minus. So now, now alpha, the off-diagonal elements are the dot product or the overlap between the two environmental states corresponding to Z plus and minus. Okay. Now, once we have this, we can go to the recipe, to the Born's rule, and measure, for instance, what is the probability of Z plus, independent of the environment, averaging out the environment. Well, we have to look at the plus plus element. The plus plus element is this one, is 1. And the probability of minus is this one. I'm sorry, 1/2 and 1/2. So we know the probability Z plus minus is 1/2. But now we know it, we integrate out, it doesn't matter the details of the only thing which, it doesn't depend on alpha either. Okay, so that's good. So now we know how to compute probabilities on kind of coarse-grained frameworks. But there is now important observation, and this is the following. Let's suppose alpha is 1. Alpha is 1 means that actually the environment didn't care about the spin, right? It means that the environment didn't change. The same state in the environment is for Z plus and Z minus. So this is like before, like the spin didn't interact with the environment. And indeed, the density rho is 1, 1, 1, 1. But this is the density of a pure state. You know, if W is 1, 1, so you take a column 1, 1 and a row 1, 1, and you get this matrix 1, 1, 1, 1. This is basically the pure state, the original W without the environment. This W, I'm sorry, the pure state, whatever, where we are. You understand what I mean? No, anyway. This W, this is the pure state, right? The pure state in the X direction. So this, if we got back this density matrix when alpha is 1 is the same as if there is no environment. But this makes sense because if E plus and E minus are the same, then basically the interaction didn't do anything. So we are still in the same W as before, in the same psi as before, okay? So we are still in this coherent pure state. We are still in the psi, which is, although we marginalized out the environment, but it didn't do anything. The spin is still in this superposition state of plus Z and minus Z. However, let's say that alpha is 0, like in our pointer state in the device. Let's say the environment, the two states are orthogonal, E plus and minus. So this is complete entanglement between the spin states and the environment state. They are really orthogonal, okay? In this case, alpha 0, look what happens. The off-diagonal elements are 0. So this density matrix has just diagonal elements. The probability of Z plus is here, probability of Z minus is here. This is the same. Once the off-diagonal elements are 0, then the system is basically the same as a classical statistical system. We lost quantum coherence. We lost the phases. We started with psi, which has a well-defined phase, +1, plus Z, and plus Z. So the phase was well-defined. But we now, after integrating out the environment, the phase disappeared. We just have a density matrix which has, just diagonal elements in it. So the strong entanglement between environment and the spin, okay, causes decoherence of the phase in the sense that after integrate out the environmental degrees of freedom, the system from now on behaves like a regular classical statistical system of the Z direction plus and minus. And you can, I don't have time to show it, but you can show it that if you now ask questions about the spin, what is the probability later on, it will just be like classical. There is no superposition anymore. So this is the essence of decoherence, quantum decoherence. Once a quantum system interacts with a classical or with complicated environment that you integrate out, if the entanglement is strong, like alpha 1 is no entanglement, alpha 0 is full entanglement, okay? So you lost decoherence. So now the question is, that's good, but what if alpha is 0.9? Okay, so you have some, you still retain some quantum coherence in the sense that alpha is not completely 0. It's not a classical density matrix where you only have probabilities on the diagonal, you only have diagonals with probability. So here comes an interesting argument, and this is the following. Until now, we just talked about a single event of interaction between the spin and this environment. And let's say it generated some alpha, less than 1. But in a real process, this is undergoing multiple interactions. Okay, so there is alpha T2 and there is alpha T3. Every time you have such interaction, you lose a little bit of the coherence by multiplying. So you get multiplication of the alphas. So imagine in the limit that Tn is large, namely that the time that of the interaction between our spin and the environment is very long. So you have this multiple, many interactions. So it's enough that each instant is generating a little bit of decoherence that the product will essentially be 0. So this is why a long process of interaction like this is guaranteed to basically erase quantum coherence and generate a density, whatever psi is. In previously it was just 2 by 2, but imagine you have some other quantum system, whatever the possible states of that component that is interacting, you will get this diagonal with the probabilities of that and 0 off diagonal, and basically it is like a classical variable. in other words, in the sense that future, you cannot choose a basis in the future which will recover that spin. You lost it. You will recover the superposition. You lost it. Okay. So that's the, yeah.
In this slide, I am suddenly confused about what is alpha. How
alpha is the outcome. Alpha is the outcome of integrating out the environmental degrees of freedom after an interaction. I'm kind of simplifying it by assuming there's kind of discrete events of interaction. Okay, so in other words, before the interaction, rho was this, because it just was pure state. Would just be, if you take a pure state 1-1, which is a mixed, a pure superposition of 1-1 with component 1-1, a row vector and a column vector 1-1, you get this is pure. But after the interaction, this went into this. And alpha is the overlap. So the overlap is the measure of the strength of the coupling between the two systems, because if alpha is 1, then nothing happened. The environment didn't feel the spin. I'm assuming for simplicity that the spin affect the environment rather than the other way around, but that's for simplicity. Okay, but if alpha is 1, then nothing happened. Okay, so we started with this, we're still with this 1-1 here. But if alpha is smaller than 1, it means that there is slight entanglement between the 2 degrees of freedom, between the environment and degrees of freedom here and there. Okay, because this state here is different from this state here, slightly different.
If alpha is 1, it's like it's like the spin is already in the framework of the environment, so to speak.
No. The environment, the framework, the original framework is Z and E. Again, I want you to distinguish between the state and the framework. This is our side. Whatever framework we are going to use, after we assume that the Schrödinger equation is such that if I start from psi, which is Z plus Z minus over square root of 2, and I interact with the environment, I get this side. Okay. Now, I choose, although you could choose other frameworks, but it's simpler to discuss, to focus our attention to the spin Z plus and Z minus, and therefore it's natural to use this environment. So I'm using this environment, okay? This is independent of the environment, but my questions about probabilities is because I'm interested what is happened to the spin Z plus after the environment. What is the probability that I'll see Z plus or Z minus or whatever, okay? So the problem is this is a joint probability. I want to integrate out the environmental degrees of freedom, okay? If E plus is the same as E minus, I don't have to do anything because basically they're independent, okay? But if they are not, then I get this alpha, okay? And the point is that the point is the following: if alpha is not 0, okay, let's suppose alpha is 1, okay? I can take this state and ask later on about spin X, right? Because I have still some information about the probability. I can choose a framework later on that talks about spin X, and I can calculate the probabilities because there is an information about spin X, because the psi is a superposition of spin X plus and minus, right? But if alpha is 0 and I collapsed everything to this, from now on I can forget about spin X. I lost track of it because I lost the quantum coherence of the original state, And I'm now purely in a classical, so to speak, system where I have a variable called SZ with a probability +1, probability -1, and I can ask what happens to that spin later on, if it interacts with the magnetic field and so on, what happens to it, okay? But I lost completely the coherence. Now, in intermediate case, it's intermediate case because I still have some coherence, okay? But now I'm saying, if you are repeating this process, multiple interactions, every such interaction will increase the coherence because it will be multiplicative. And then after many such interactions, you basically end up with a quantum variable, whatever it was. If you started with Z, it will be Z, depending on the coupling of the environment and your framework. But now here we chose a reasonable framework because we assume that this Z, you know, generates Z plus and Z minus. We just assume that. So it's natural to ask about Z variable and whatever it is, but other systems will be different. Okay. So basically what I mean by that is that now you can fantasize that in more realistic situation, you start with a system where you have locations and momenta, and you have a superposition of two locations. You don't know anything about velocity because it's quantum, and you interact with the environment, and etc., etc. But then after this kind of story, you will end up with the classical like coordinates X, kind of the same, you know, the same spirit. Okay. Again, there is a whole Torah, the whole about that, how you do it, and so on. I don't want to. It's not. I don't want to go into. Just to give you the insight, that the details are complicated. All right. However, with this interpretation. Oh wait, fine. Okay. Sorry. So now it's 5 o'clock already. Let's stop here. Okay, so the conclusion is the following. There are two things. One, going from micro to macro. One thing is that when the system interacts within a macroscopic and you are asking a system and you are asking a question which you as a macroscopic being, you want to make sense of that. You want to make sense of your measurements and so on. There are preferred frameworks and non-preferred frameworks. That's one. Okay. The second one, even the preferred framework are not pure states, because this is naively a preferred framework, ZE. This will be like a pure state. You just look at this and you look at this and so on. But the preferred framework is integrating out, is coarse-grained. You want to integrate out all these complicated quantum degrees of freedom of the macroscopic big environment, as we said in the classical case. Next time, tomorrow, you'll do the same experiment. The states will be different slightly. You don't want to bother about them, so you want to coarse-grain. So the preferred ones are also coarse-grain. Once you coarse-grain, you start to lose, you're likely to lose the coherence because of the interaction. And that's the story, okay? And once you lose coherence, the probabilities, the system behaves as if it is a classical system with some probabilistic description. Like we have here, probability of the Z plus 1/2, the Z minus 1/2. But it's like a classical system. There is no off-diagonal element, which are kind of the phases. All right, let's stop here. Take coffee or tea, or light candles if you have time. Let's 5 minutes. Let's reconvene at 5:15. Okay. ספיר, יהיה לך זמן
לא הגעתי לזה עדיין, הייתי תקועה עם השיעור הקודם. אבל האמת שחזרתי אליו עכשיו, אני חושב שנפתח פרק שלם של עוד שאלות בנושא אחר.
Okay, that's good. So that's a very qualitative story, and I must say it's not only also because of short of time, but also because the story itself is only partially understood in the sense that physicists came up with models of how particle interacts with a given environment, but there is no yet agreed upon, more quantitative general. Okay, that's good enough. Okay, however, from this analysis that I mentioned here, we gain something, but that it's not only that we understand how decoherence happens in a kind of macroscopic situation, but also we understand that it takes time, because a very brief interaction will do some decoherence, but will not completely. There is no reason why E plus and E minus will be completely orthogonal, that the interaction will be so strong that a single very brief interaction will already wipe out the phases. It will take time, like shown here. So this is interesting because it says that even on the classical realm, something which, again, like our spin interacting with balagan, macroscopy, if we are doing a very fast measurement, we might see coherence because there was no time to lose the coherence, the quantum coherence. Okay, so this raises the question: what is the decoherence time? And it's an important question. We'll ask this about brain. Quantum computing is now a very hot topic. And quantum computing is all using this superposition, the fact that you can take a qubit and write it in terms of superposition of plus and minus. And if you have 8 qubits, you have, many superpositions like that. And the fact that you can do the computing in parallel by applying this unitary transformation and so on and so forth, all this relies on the fact that you are keeping this coherence. Otherwise, you backed into 8 classical bits and you don't gain anything. Right? So this is a big thing today. It always was, but today even technologically, it's a big thing. The decoherence time and how to find against it. Okay, so I'm not. So there is an interesting, very nice paper by Tommy Leggett and Calderia. It's a series of papers, but you can look at Physical Review in 1985. Lots of you. But anyway, they have a simple model. The model is you have harmonic oscillator, quantum oscillator, with size L and some mass m. And let's say it interacts with the environment, which are collection of many other oscillators, but with temperature T and okay. And now in this system, there is you can analogous to what we wrote down in statistical dynamics. We said that you have like an equations that, unlike a Newton's equation, you have a dissipative term, remember, proportional to velocity, and then there is a noise term. Okay, the dissipative term is like viscosity, like chikuk. It will cause a dissipation of energy, loss of energy, and it will tend to basically go to the minimum of the potential. And however, if you have noise proportional to temperature and so on, then you'll get a competition between the two. So you can write down, a quantum analog of that. And again, the quantum system, when it interacts with this feedback, there will be 2 processes. One will be loss of energy to the feedback of the quantum harmonic oscillator. And the other one will be this dephasing, this noise which will decohere the quantum wave function in the quantum state. Okay, so there is one time constant. It's called tau r, which is relaxation time, which is the time, let's say, it's zero temperature, time in which the quantum system will lose its or low temperature will lose its energy to the environment and go to the minimum. So imagine you take a harmonic oscillator in a superposition state. One component is the rest state, and another component is a size L displacement of the mass in the spring, a wave packet with the distance L. Okay, this is what I mean by size L. So it's a superposition, and now we want to let go, and we want to know how long it will take until it will lose all its quanta and go back to the ground state. If it was zero temperature, this is tau r, relaxation time. It's complicated to compute tau r because it depends on the strength of the coupling between the environment and the nature of the coupling. Is it linear in X, quadratic in X? So there is a whole detail. It really depends on the details of the mechanism of interaction between this quantum oscillator and the environment. Okay, this is tau r, relaxation time. Another time is tau d, is the dephasing time, kind of the noise, how fast or how strong the noise operates on the phase. This is our alpha, the tau, this is this time, the time that it takes alpha to go to essentially zero. Okay, now it turns out that you can show under general conditions for some range of model systems that there is an interesting relation between the two. Tau d coherence is tau r, proportional to tau r, to the relaxation time. Makes sense, because if the coupling is strong, the coherence will be, this will be the time constant that will enter there. And then times something which is the wavelength, de Broglie wavelength. Those of you that studied quantum mechanics know that every system has some wave pack has some width. Even an electron is not a point. It has quantum wave packet. So this is the quantum wavelength, the spatial extent of the coherent wave function divided by the physical size, okay, squared. And then the Broglie wavelength, this is classical textbook formula for what is the quantum wavelength effective coherence extent of the wave function if there is a mass and there is temperature T, and this is a Planck constant and 2 pi and so on. Okay, so this is this ratio squared. Now this is very important relation. Why? Because the Broglie length, okay, this is a very simple, you can plug in temperature and mass and everything is known. And tau r is easily measured. Tau d is how to measure. You need a quantum system to be able to be sensitive to the phases. It's very hard. But relaxation time, you just measure the rate of loss of energy. So that's easy. So this relation is extremely important. And let's take an example. Suppose I have an electron. So you can, room temperature, you can take the parameters and put this, and you find that the Broglie wavelength of the electron is 10 to the minus 7 centimeter. And now the length, well, let's say an electron in an atom, orbiting around an atom. So the size of the atom is 10 times smaller than that. So the ratio is 1, bigger than 1. So this means that it's really the wave aspect of electrons cannot be ignored, okay, because this ratio is big. Let's take another extreme, a 1 micron size dust particle. You can find out, what is the mass of it and so on. I just plug in the numbers, and I got the lambda is 10 to the minus 15 centimeters. Extremely negligible wavelengths. What I mean negligible compared to its size, micron. It's 10 to the minus 11. So basically, you can ignore the decoherence time will be so fast. There is no meaningful a duration of time where you can say this dust of micron-sized dust is quantum in terms of coherence. Okay. Good. So now, okay. So that's basically the way you can take any system that's well characterized, a quantum. So everything is quantum, but you can see that depending on, there is a mass here and let's say room temperature, but of course if you can cool it to very low temperature, again lambda will be high. So you can see how the temperature, how the mass, how the size L, all this, how it affects the coherence, the decoherence time, at least relative to the relaxation time. So that's a very good set of thumb rules to decide whether how fast the thing will decohere. So you can imagine now that if I want to build a quantum computer, I'll have to work out, maybe I'll cool it to super low temperatures, and I'll work hard on the tau R. I'll do, I isolate it from noise, making the coupling very small, so the relaxation will be very long, etc., etc. Okay, I want to go back to the brain now, and ask about quantum in the brain. This is a question that many years has been raised in the literature from the dawn of quantum mechanics. Okay, people said, well, free will, quantum mechanics, free will, it explains free will. Even when I was a student in the 70s or early 70s, I disclose my age maybe, but anyway, it's not the same framework, so I'm not allowed to guess my age. But anyway, when I studied quantum mechanics, that's what the teacher said. My teacher said, free will, quantum mechanics explains it. So this is what philosophers talked about it, and so on. And maybe in modern era, popular science, Penrose, in his famous book, The Emperor's what's it, Empty Mind? What was it? Right? Ariel, the Emperor's
mind, no? I think
the
mind.
Emperor's Empty Mind?
No, not empty. Just
not empty. The Emperor's New Mind. Oh, no. What was it? Okay, anyway. Good. So anyway, so he suggested about consciousness and so on, that the brain, the cognition, some aspects of cognition, cognitive processes are based on coherence wave functions inside microtubules in nerve cells in the brain. And since then, there's arguments, and still it is still came back to the fore, largely also in part because of quantum computing. Hey, we have quantum computing, the brain is computing, maybe neurons are like qubits, maybe they're doing quantum computing, etc. So that's a very, very, very popular question, and we have to address it. Okay, so before giving you answers, I want to elaborate on the questions. People ask, is the brain classical or is the brain quantum, or are the neurons classical quantum? So I want to, whenever people ask such question, is my iPhone quantum or classical or whatever, there are three aspects to the question. I just want to elaborate the question. One is structural aspect. By this I mean, are a given physical system structurally made of classical things or quantum things? Okay. And another one is kind of more dynamics, the coherence. And the third one is the indeterminism, the probabilistic aspect, the stochasticity. And they are related, but very different. So let me just take the first one, structural aspect, and wipe it out of the Seder Hayom, of the agenda. Okay. The brain is quantum because everything is quantum. My car is quantum, my desktop is quantum, my coffee is quantum, every wire in your machine or in house quantum, regardless of the size of it, because it's made of atoms, and atoms are not stable without quantum mechanics. In other words, what it means that the brain is quantum, it means structurally, it means, can I describe a piece of matter, macroscopic matter, without the principles of quantum mechanics? And the answer is no, regardless of the size, because every macroscopic thing is made of atoms and protons and electrons and so on. If you just use classical physics to explain it, you cannot, because atoms will collapse without quantum mechanics. So the stability of matter is basically relying on quantum principles. Pauli principles, fermions cannot occupy the same state, etc., etc. I don't want to get into entire quantum physics, but it's silly to say, well, the brain is classical without elaborating what it means. Everything is quantum. If you think about neurons are made of ion channels and proteins. Proteins have electronic states. Once you go to that level, without quantum mechanics, you cannot make sense of anything. Okay, so we are quantum mechanical things like everything else in the universe, as far as we know, down. Okay. But that's not interesting. Okay, we have quantum mechanics. We understand how atoms are stable. We understand, the atomic processes, the electronic transfer. We understand that. The more meaningful question is whether the scale of energy changes in space and time when we talk about neural processes are meaningfully quantum. Okay, that's the question. And here there are two things. One is, as I said, coherence, and one is stochasticity. Okay, so so let's talk about stochasticity first. Okay, and again, why? Because one thing you can say the following. So quantum mechanics, even in the consistent quantum theory that I described, it's an axiomatic statement that quantum system is probabilistic. You have wave function with several branches, and you have frameworks and so on, and then things are probabilistic in general. Okay. However, if you take many independent spins and aggregate them, then the stochasticity will be wiped out. So I discussed decoherence, but I didn't discuss about stochasticity. But stochasticity is another thing, right? You have quantum indeterminacy. Okay, fine. We succumb to it. We accept it with natural piety, as the philosophers say. However, when you aggregate many of them, if they're not strongly correlated, you will wipe out this quantum fluctuation. So a simple empirical question is the brain sensitive to quantum fluctuations? Not necessarily coherent, not coherent, but just simply the probabilistic aspect of quantum mechanics. Because you might argue that the brain is composed, the processes in the brain composed of many atoms and millions of atoms. And it's simply not, and there is noise and there is all kinds of things. It's not sensitive to the minute quantum fluctuation. And I think, so interestingly enough, this is experimental question, which turned out to be interesting and have interesting answers. And one of the answers came out from measurements of visual acuity or visual sensitivity of the visual system. So already in the 40s, researchers discovered that behaviorally, our perception, visual perception, can detect single photons. Now, when you are looking at a source of light, then as a classical element, it has an intensity. The intensity is deterministic, obeys Maxwell equations. and you're not sensitive, but if you look at a very weak source of light, then it becomes quantum and there are photons, and the photons are Poisson statistics. So the number of photons, or even when if there is a photon or not, for a given intensity of light, that will be quantum fluctuation. Okay, so you can ask, what happens if I'm exposed to a I'm dark adapted and I'm exposed to a very weak source of light with a given fixed intensity? Am I sensitive to the random fluctuations of the number of photons that impinge on my retina? And the answer, and interestingly enough, if you look at the, you do a signal detection experiment, and you, as a function of the number of photons, you see kind of a probabilistic curve, and the probabilistic curve, you can fit it to some thresholds, and you can find out that we are sensitive to 2 or 7 or 12 number. That we are sensitive to the fluctuations in the number of photons. So if only 2 photons, below 2 photons, we are sensitive, and so on. So that already was surprising, that our machinery in the front end must be somehow sensitive to a small number of photons in such a way that the brain doesn't mess up with it, that it's amplified, that even perceptually. So that's a very big thing, that we are perceptually sensitive to the fluctuations in the arrival of photons. Okay. A more modern version of that, you can look at the Nature Communication paper about 4 years ago, which did it in a nicer way. They actually were able to just control the number of photons. That's a single photon or not a photon. And they showed behaviorally that if you did, in some cases, no photon, other cases, 1 photon, then subject may guess the 2 alternative for choice. The reliability most of the time is bad. R1, R2 are confidence rating, and most of them are weak. And a fraction of experiment, a subject would say, yes, I saw and I'm very confident. R3 is high confidence. Most of the time, I don't know, I'm guessing. But in some fraction of the time, subject said, I saw light and I'm highly confident. This is R3. Now, if you look on only these cases and you correlate it whether there was a photon or not, you see above chance, substantial above chance. This high confidence is 60%. Chance is 50%. Okay, so it means that you can really above chance detect single photons. So that's kind of a modern version of this experiment. And then more recently, not more recently, but also recently, people actually have measured the quantum efficiency of the photoreceptors themselves, and they find in this paper that the quantum efficiency of the rod cells was 30.29, about 30%, remarkably similar to estimates of human rod cell quantum efficiency based on behavioral experiment. So this is now direct biophysical measurement of the quantum sensitivity of the rods, of the photoreceptors. And here you can see the current generated by the photoreceptors upon arrival of a single photon versus no photon. It is a slow response, second long, but nevertheless, there is a clear signal just by a single photon. Okay, so that's good. So we now have behavioral evidence, and we have also biophysical explanation of the mechanism, how, at least at the level of photoreceptors. We don't know, I don't know if there is any careful experiment that measured what happened to these tiny currents as they propagated to the visual cortex and so on, but they must do something because it affects the behavior. So that's a remarkable experiment. evidence that to me means that that you can have extreme situations, but still you can have situations where our perception can be sensitive to quantum fluctuations, like how many photons, or did the photon arrive or not arrive. It's a quantum fluctuation. Okay, so that's interesting. Okay, now here there are more of this. Okay, but now you want to go to the coherence, because many of the talks about quantum brain were really advertising that it's not only that there is some source of quantum noise in the brain, but it's also that there is this coherent, this bizarre aspect of quantum mechanics where you have superposition and you keep the coherence of that. It is something that is relevant to the brain. And here I'm by far more skeptical, okay? And here I'll give you an example. Take an ion channel, an ion pore. You know, what I'm doing is the following. So there is no, as I said before, there is no question that over a very short period of time, all processes will be a quantum and will have quantum coherence associated with them. The question is for how long, for what duration. If you take, let's say, action potential, and a single neuron generating an action potential, it's kind of a millisecond time scale, maybe 15, so, 0.1 millisecond or whatever. But it is an accumulation of many, many ions, ion channels. So let's look at one ion channel, opens and closed. An ion channel, if you put numbers, the mass and again, room temperature, the brain temperature, you get 10 to the minus 10 centimeters. And the size is, you know, nano or something like that. Anyway, so you get 10 to the minus 4, the ratio of wavelength, quantum wavelength, spatial coherence over the size of the ion channel. And if you put it, then you get that it's the ratio between tau d and tau r is 10 to the minus 8. Now, tau r, the relaxation time of ion channels is slow, is milliseconds at best. This is fast, okay? So you get 10 to the minus 11 seconds for the tau decoherence. Well, some say it's even 10 to the minus 13, but nobody can come up with a story where this will be substantially larger. Okay? So to me, it means that, of course, everything, all processes on a very short, on a very small length scale and a very, all matter are consisting of quantum elements, and all time can be broken into very tiny pieces, and all space can be broken into very atoms and electrons and so on. So of course, it's quantum. Everything is quantum. Like my car engine is also quantum. However, if you ask whether this coherence can be relevant to the time scale of millisecond, or tenths of a millisecond, or other microseconds, whatever, any reasonable time over which our cognition works, okay, you find it's completely negligible. So I think all these stories are simply stories, they're not science. So this is my conclusion for today. And the conclusion is the following. Maybe, okay, this is maybe the, okay. So structurally, everything is quantum. Okay, we discussed it, okay? Probabilistically, the brain does show, or behavior, maybe next time I'll show it, but behaviorally, perceptually, our cognitive functions and our actions, our behavior, does show substantial degree of stochasticity. So any psychophysical rules or any laws in cognitive neuroscience will be probabilistic, will be given this stimulus and given these conditions, what is the probability that they'll do this or do that? And there is ample empirical evidence for that. And therefore, any sensible science of the brain or cognitive neuroscience must cope with that, must explain where this stochasticity comes from. And there are many, many sources. Neural noise, by mean, I mean biophysical properties, which are not quantum necessarily. Thermal opening and closing, blood temperature fluctuations, mostly environmental fluctuations. We move around the world, things change, we move our eyes, the environment changes, and so on. In addition, there are two more exotic. One of them is completely intrinsic, chaos, which we discussed a few weeks ago, which is intrinsic in the sense that even without environment, just take a circuit, a neural circuit with strong nonlinearity and competition between inhibition and excitation, you'll get fluctuation. And if you start from different initial conditions, you'll see different, you might see source of it. And then, as I showed today, there are extreme cases where you can isolate purely quantum fluctuations to be the source of the stochasticity, even in the perception. But I think this is rare, but still it is there. And now some people would say, well, you think it is there, but maybe it's not rare. Maybe when you have a decision-making process and the brain contemplates whether it is to do A or to do B, maybe there is some sneaking in some quantum fluctuations for very, although only one channel or something, quantum fluctuations, and this will be amplified and so on. It might be. But we cannot rule it out because we know for a fact that there is in the brain a machinery to take a quantum fluctuation, sorts of fluctuations, and to amplify it to perception. Okay, that's fine. So there are ample source of fluctuations. Some of them might be quantum in nature. Moreover, I want to say something that more general. When we talk about classical, we talk about system interacting with thermal fluctuations and so on. There is no simple way to ask whether thermal fluctuations are classical or quantum. Because after all, as I said, we are quantum in the basis. So, okay. However, it's important to say it's decoherent. Once it's decoherent, it acts like a classical fluctuation. So photons, if the source of light is decoherent light, those of you that have some engineering or some optics, they may know what I mean. Maybe Chanwu is an engineering school. Okay? So if the light is decoherent, or if the light is decoherent through the interaction with our photoreceptors, as I described, then although the fluctuation that started with the number of photons, which is purely quantum source of fluctuations, it behaves like a Poisson source of balls that I generate. There is no difference between its quantum nature or it's just a source of fluctuations, whether it's quantum, classical, who knows? Okay. Metaphysically, we are interested. Why? Because we say if it is not quantum, then it's coming from some other sources in the environment. So the universe as a whole is deterministic. If it's quantum, then it means that even the universe as a whole is not deterministic. So philosophically, metaphysically, it is an important issue, but there is no clean scientific way to look at the fluctuations in the neural activity and to say quantum, classical, it's all okay, channel noise, quantum that. It's elusive. You could ask whether it's coherent by careful measurements of coherence, some superpositions and so on. But that I believe is out of the question. Okay, that's more or less summarizes what I what I can say, or at this point, about quantum and the brain. We'll come back to these issues when we discuss free will and determinism and so on. I think that Ariel, remind me correct me if I'm wrong. This basically ends the physical part, right?
Yeah, yeah.
The strictly physical part, almost. Okay. What we'll do for the rest of the course, we will discuss implications to mind and brain connections, and that will take us to a series of kind of boundaries between physics or between science in general and philosophy, how to make sense of this, what are for scientists, what are the options that are available to us in conceptualizing or discussing mind-brain relations. All right, any questions on this? I just want to add, you might ask, you might wonder, why did I go through the consistent quantum theory and so on? And I just want to explain why I went through this. First of all, I love this part. Okay, but also because if you don't make sense of quantum mechanics, it's hard to even understand what is the question about the brain. For instance, if you take the position that the basis of quantum mechanics assumes a conscious observer, so consciousness is part of quantum mechanics, then. So I think I had to demystify quantum mechanics, make sense of it as a purely scientific description of the world. It's bizarre, but it doesn't need an observer, doesn't need consciousness and so on. It's physics like classical physics, although it's bizarre. Then we can ask, in a more rational way, how it affects the brain. So this is why this is the journey that I had to take in order to discuss quantum in the brain.
I have a question.
Yes, please.
So you have the decoherent quantum fluctuations in this list, but do I understand correctly? It's never like, we don't say that it's the ions or anything in the brain. It's just that we can see fluctuation, like in extreme cases, we can see quantum fluctuations in the environment. So quantum mechanics is like not an answer here to sources of fluctuations in the brain. It's not like neural noise, right?
I agree, but there is no evidence that intrinsic quantum fluctuations affect perception. I agree with you. I don't know of any evidence of that. But But this is still a proof of existence, of feasibility proof, because the fact that there's two things. One is that the sensor apparatus is very sensitive, has high efficiency, but then moreover, that is being able, the brain is amplifying it such that it can affect perception, despite the fact that there is all this noise in the brain that goes on again, So I agree with you, but that's one point. Another point is the following. To me, the metaphysical importance about quantum mechanics in the brain is the issue of indeterminism, okay, versus determinism. So metaphysically, if the fluctuations, even if they come from outside, but they are quantum in nature, then it means that we cannot say that our cognition or perception is deterministic, because the next time I'll repeat the same, very same situation, but I'll do something else, because the universe, suppose I'm coming back to the same universe. Will I behave similarly? Will I behave deterministic? What is determinism?
But
Determinism
it's
says the
deterministic,
following,
but it's
okay? I made a decision, okay? Was I forced by scientific laws to make that decision? How do I measure it? I'm asking, suppose I recreate the same situation again. Will I behave similarly or not? So according to classical physics, the answer is yes. If you will recreate the state of the brain and the environment again, you'll do the same. Here is an example where the answer would be no, not necessarily. I recreate the same physical situation again. I'm including the environment as part of the situation. Okay?
But it is deterministic in the sense that
you can say I see you're saying okay.
You see the observable, right? You see whenever there's like this an observable of the photon, you see it. It's deterministic, right?
You could say that. You could still argue that a weaker sense of determinism, that although the universe as a whole is not deterministic, but if you recreate the state of the brain, or taking into account you freeze the fluctuations that impinge on the brain, then it will be might be deterministic. It's possible, and I agree. Okay, I hear what you're saying. It's a valid point. Okay, it's possible. But again, there is an empirical question, which I don't know the answer to, whether there is an evidence. I don't know of even an empirical, or I don't know of an empirical. There is another sensory-induced claim about sensory-induced sensitivity in the olfactory system. That again, I think it's the olfactory neuron receptors, which may be highly sensitive to quantum fluctuations. But again, it is sensitivity of the sensory apparatus. Whether there is, I don't know of any empirical evidence that something which is more intrinsic to the brain can be sensitive to quantum fluctuations. We know, you can even ask the following question, whether the action potential, the firing of a neuron, a single neuron, is sensitive to the individual fluctuations of channel opening and closing. We know that most of our theories, models, take I don't know, Hodgkin-Huxley models. They're all deterministic models, right? They just say there are some linear currents and so on and so forth. But we know that individual ion channels are fluctuating. And there are researchers that estimated or measured this effect on the fluctuations in the firing time of single neurons. And you can look at the very, very small changes in the firing jitter and the firing of a single neuron, even in the lab, where everything is controlled. And that's probably due to fluctuations of small number of ions. So you can see a small jitter in the action potential timing. However, even that is rare because, okay, so, you know, action potential, a small jitter and action potential will not do in normal circumstances anything to our perception. But more than that, you can ask whether these channel fluctuations are quantum. Typically, they're thermal, they're described by thermal theory. So it's not, as I showed you, even an ion channel, single ion channel. First, for decoherency, definitely, but it consists of many atoms and electrons. I don't know. So there are debates in the literature. What is the right way to describe channel opening and closing fluctuations? Whether they are really whether there is some reminiscence of quantum fluctuations or not. So are they intrinsic, as you said, right? Or they are, again, interacting with the environment in the brain. So all these questions, which I don't know if there is a clear answer to them, but it's a valid point.